Welcome to the Deep Dive. If you're anything like me, you probably feel like you're constantly swimming in this flood of new representation learning papers. It can be pretty overwhelming.
Oh, definitely. It's hard to keep track, let alone see the connections.
Exactly. But today, we're looking at a paper that honestly feels like it might be a bit of a Rosetta Stone for this whole area. It offers this surprisingly elegant way to connect a whole bunch of different techniques.
That's the one. We're diving into ICON, a unifying framework for representation learning. The core idea is really powerful. A single information-theoretic equation that sort of generalizes many, many modern loss functions.
A single equation. Okay, that sounds promising. It links supervised, unsupervised, self-supervised, all of them.
That's the claim, yeah. It reveals the shared principle behind methods that, on the surface, look quite different.
Okay, so for listeners maybe just tuning in for a minute, what's the absolute core takeaway? The elevator pitch.
All right, quick version. ICON basically shows that all these techniques, think clustering, dimensionality reduction like TSNE, contrastive learning like SIMCLR, even standard supervised learning, they're all fundamentally trying to do the same thing. Minimizing an integrated KL divergence. It's about making sure the relationships your model learns between data points, this learned distribution, match up with the relationships you want it to see, the supervisory distribution.
Okay, aligning desired relationships with learned ones.
Exactly. And it's not just theory. This framework led them to develop new approaches that achieve state-of-the-art results in unsupervised image classification, big gains on ImageNet, and it also gave them principled ways to debias contrastive methods.
Impressive. So our mission for this deep dive is pretty clear then. We're going to unpack ICON, figure out what it means for, AI researchers, ML engineers, anyone trying to build or just understand these representation learning models.
Right. We want to see how it connects the dots and maybe what new ideas it sparks. And just to be clear, everything we're discussing comes directly from that ICON paper by Al-Shamari and colleagues.
Perfect.
Yeah.
So let's get into the heart of it. What's the central concept we really need to grasp?
Okay, so the fundamental idea, as I mentioned, is minimizing this Kullback-Leibler divergence, the KL divergence.
Right.
But it's between two specific things. These conditional neighborhood distributions, think of them as defining transition probabilities between data points.
Transition probabilities, like the chance of hopping from point I to point J?
Exactly. You have one distribution, Pfeita, which is the supervisory one. This encodes how you want points to be related, maybe based on labels or proximity or augmentations, whatever your task defines as neighbor.
Okay, that's the target.
Right. Then you have the learned distribution, Q5 Q. This reflects how the model, based on the representations it's currently learned, sees the relationships. So maybe points with similar embeddings get a high probability here.
And ICON says learning is about making Q5 look like Pfeita.
Precisely. The loss function is literally the integral across all starting points I of the KL divergence between Pfeita given I and Q5 given I. You want to minimize that total mismatch.
So you're summing up how much the learned neighborhood around each point differs from the desired neighborhood.
You got it. And usually Pfeita, the supervisory part, is kind of fixed or at least defined by your setup. The learning happens by adjusting the model parameters, like a neural network, which in turn changes the embeddings, and therefore changes Q5 to better match Pfeita. Figure 2a in the paper has a nice visual for this alignment.
What about learning both? The paper mentions that's possible, but maybe not ideal.
Yeah, mathematically you could try to learn both Pfeita and Q5, but there's a danger of trivial solutions.
Trivial solutions, like what?
Like both distributions just collapsing to something simple that matches perfectly but doesn't actually capture any useful structure from the data. Keeping Pfeita anchored, based on some external signal or assumption, forces Q5 to learn something meaningful about the data itself.
Okay, that makes sense. Now this periodic table idea in Figure 1, that looks ambitious. Unifying 23 methods, how?
It sounds crazy, but it works because the framework is so flexible in how you define those Pfeita and Q5 distributions. By choosing different mathematical forms for them, different families of distributions, you can recover all these different algorithms.
So the specific math you plug in for desired neighbors and learned neighbors determines which algorithm you end up with.
Exactly. Figure 2b shows the main families they use for these distributions: spatial, discrete, cluster, and graph. Each one captures a different kind of relationship.
Let's break those down a bit. What's the spatial family about?
Spatial is often about, well, space, proximity. So Pfeita might be based on k nearest neighbors in the original high-dimensional space points, close together are desired neighbors. And then Q5, the learned part, might involve fitting a Gaussian or maybe a T distribution around the low-dimensional embeddings. Think SNE or TSNE.
Right, preserving local structure. What about discrete? That sounds like labels.
It often is. For the discrete family, Pfeita could say points with the same label are neighbors. That's supervised learning. Or in contrastive learning, it might say different augmentations of the same image are neighbors.
Okay, so SIMCLR fits there.
Yep. And the learned Q5 would then involve things like predicting class probabilities or, maximizing the similarity, like cosine similarity between embeddings of things that should be neighbors, according to Pfeita.
Then the cluster family. Is that for things like k-means?
Exactly. With the cluster family, Pfeita often reflects that intuition that points physically close together should probably be in the same cluster. So maybe it uses a Gaussian based on original distances again.
And Q5?
Q5 then represents the model's actual cluster assignments. Like, it might assign a high probability if point I and point J are assigned to the same cluster centroid. Minimizing KL makes the assignments align with the spatial closeness.
Okay, that covers clustering. And finally, graph, for graph NNs and things.
Right. If your data is a graph or you build a similarity graph, Pfeita could be based directly on the graph edges, linked nodes, or neighbors.
And Q5 tries to make embeddings similar for connected nodes.
You got it. The learned embeddings Q5 should reflect that connectivity defined by Pfeita.
Wow, it really is versatile. And Table 1 in the paper is the key, showing the specific Pfeita and Q5 choices that would cover all those 23 methods.
That's the one. It maps specific distribution choices from these families to methods like SNE, UMAP, SIMCLR, SUPCON, K-means, spectral clustering, InfoNC, all sorts of things. The math details are in the supplement, but the table gives you the overview.
Let's walk through a couple of examples just to make it concrete. How does SNE, stochastic neighbor embedding, fit in? The whole neighbors remain neighbors idea.
Okay, so SNE wants to learn low-dimensional embeddings, that's the phi part, from high-dimensional data X. The supervisory distribution, P theta G, uses a Gaussian centered on each high-dimensional point I. Points J closer to I in the original space get higher probability.
So P theta captures the high-dimensional neighborhood.
Correct. Then the learned distribution, K theta G, uses a similar Gaussian but centered on the low-dimensional embeddings of I and J.
Okay.
Minimizing the KL divergence between P theta and Q5 forces the low-dimensional embedding distances to reflect the high-dimensional distances, preserving that local structure.
In TSNE.
TSNE, as Corollary 1 points out, just swaps the Gaussian in Q5 for a heavier-tailed student's T distribution. Helps separate clusters better, usually. But it's the same core icon principle.
Okay, clear. Now, SIMCLR, contrastive learning. How does icon frame augmentations of the same image are neighbors?
Right. So for SIMCLR, the supervisory signal P theta is different. It basically says, if image J is an augmentation of the same original image as I, then P theta G is high. They're neighbors. If they come from different images, it's 0 or very low.
So relatedness defined by data augmentation.
Yep. Then the learned distribution, Q-phi, is based on the similarity, usually cosine similarity, of their learned embeddings in the latent space. A common choice makes Q-phi look sort of like a soft max over similarities.
And minimizing KL.
Minimizing the KL divergence here means you want high similarity, high Q-phi, precisely when P theta says they should be neighbors, i.e. they're augmentations of the same image. It pushes embeddings of related views together. SUPCON just extends this to use class labels, too.
It's fascinating how it reframes these objectives. What about a classic like k-means clustering? Points close together are in the same cluster.
Yeah, for k-means, you can think of the supervisory P theta G, again, using something like a Gaussian based on the original distances nearby points should be related. The learned distribution, Q of I, then reflects the actual cluster assignments made by the algorithm. It could be, say, 1 if I and J are assigned to the same cluster, and a 0 otherwise, or a smoothed version.
So minimizing KL aligns the cluster assignments with the original spatial proximity.
Exactly. It encourages the algorithm to put points that were initially close into the same cluster. Theorem 13 even connects the standard k-means objective to icon by showing an implicit entropy term that encourages firm assignments, which fits this framework.
Seeing these connections is really illuminating, but the paper doesn't just stop at explaining existing methods, right? It uses icon to create new things, especially around debiasing.
That's a key contribution, definitely. A good framework shouldn't just describe, it should enable new discoveries. And they use the icon perspective to develop some clever debiasing strategies, particularly for contrastive learning where noisy negatives can be a problem.
Right, the issue of accidentally picking negative samples that are actually semantically similar. How does icon help?
It suggests modifying the supervisory distribution, Pfeita. Instead of having Pfeita be absolutely certain about which points are neighbors, positive, and which are not negative, they introduce some uncertainty.
Uncertainty, how?
They propose mixing the original Pfeita with a uniform distribution. So the new supervisory signal, P tilde, is like 1 alpha times the original Pfeita plus alpha times a uniform probability over all points.
So even points you thought were definite negatives get a tiny bit of neighbor probability from the uniform part.
Exactly. Alpha controls how much uniform noise you mix in. It stops the model from becoming totally overconfident that a chosen negative sample is truly different, acknowledging that maybe it's not. It's analogous to label smoothing in supervised learning.
Like softening the target.
Precisely. And they relate this to why the heavy tails of the t-distribution in TSNE work well. They implicitly give some probability mass to points that are further away. This debiasing helps handle those potentially misleading negative samples.
Interesting. And there was a second debiasing strategy mentioned, neighbor propagation.
Yeah, that one comes more from the connection to graph methods and spectral clustering. The basic idea is to expand your definition of the supervisory neighborhood Pfeita. Instead of just using immediate k nearest neighbors,
You look further?
you take short walks on the nearest neighbor graph. So neighbors of neighbors also become part of your supervisory signal. They define a smooth distribution based on powers of the adjacency matrix. P plus P2 plus PK.
So it densifies the supervisory signal.
Right. A simpler version just says any point reachable within k steps is considered a neighbor with uniform probability. It broadens the context beyond just the absolute closest points, making the supervision potentially more robust.
Both sound like ways to make Pfeita less brittle, more nuanced. Did they test these ideas? The experiments focused on clustering, right?
They did. They focused on unsupervised clustering on ImageNet1K, which is notoriously hard. They used features extracted from pre-trained DynoVision transformers VITs.
Okay, strong baseline features. And they evaluated using Hungarian Accuracy.
Correct. Hungarian Accuracy matches predicted clusters to ground truth classes. Their own method, derived from these icon principles, is called Infone's clustering.
And what did Infone's clustering involve?
For its supervisory neighborhood, Pfeita, it used a mix. Augmentations of the same image, like contrastive learning, the immediate k nearest neighbors, K3, and neighbors found by one-step walks on the KNN graph.
Combining different neighborhood ideas. And the learned part, Q5.
Q5 was based on shared cluster likelihoods derived from running k-means on the embeddings.
So how did it do? Especially the debiased Infone's clustering.
It performed extremely well, consistently beat other state-of-the-art unsupervised clustering methods like TMI, SCAN, IC across different sizes of VIT models.
That'd be specific numbers.
Yeah, the gains were pretty significant on the bigger models. Compared to TMI, which was a strong baseline, their debiased method was plus 4.5% better on VIT base and a really impressive plus 7.8% on VT large.
Wow, nearly 8% improvement on VT large is huge for ImageNet clustering. Why did it work so well?
The authors point to a couple of things. First, the loss derived from icon seems to be somewhat self-balancing, needing less manual hyperparameter tuning. Second, it effectively brings insights from contrastive learning, like using augmentations, directly into the clustering objective in a principled way.
Makes sense. What about the Ablation Studies? Did they confirm the benefits of debiasing and neighbor propagation?
They did. The ablations were quite thorough. For debiasing, they varied that alpha parameter, the mixing coefficient. They found performance consistently improved with debiasing, peaking with alpha around 0.6 to 0.8.
So adding that uncertainty definitely helped.
Yes, and interestingly, applying it to both the target Pfeita and learned Q5 spaces often gave the best results. Figure 5 also showed it improved performance and calibration across different batch sizes, which is important practically.
And the neighbor propagation. Did adding neighbors help?
It did. Including the direct KNNs and short walks, like length 1 or 2, gave a solid boost over just using augmentations. However, really long walks seem to give diminishing returns, maybe diluting the signal too much. Table 3 summarizes all these effects, nicely debiasing, KNNs, walks, they all contribute.
Great to see that level of analysis. And they showed that debiasing wasn't just for clustering. Appendix A looked at feature learning too.
Exactly. They briefly showed in the appendix that applying the same uniform mixing debiasing strategy during standard contrastive feature learning on datasets like CFAR and STL also led to improvements.
How were those measured?
Through better linear probing accuracy and KNN classification accuracy on the learned features. Tables 5 and 6 show those results. And Figure 7 has some nice TSNE plots suggesting the debiased features form cleaner clusters.
So the debiasing principle derived from ICON seems quite general.
It seems that way, yes. Reinforces the value of the framework.
Okay, this has been a fantastic deep dive. To wrap things up, what are the absolute key takeaways for people listening?
I think the main thing is that ICON offers this really unifying lens on representation learning. It shows this common objective, minimizing KL divergence between how we want neighbors defined and how the model learns neighbors underlies a huge range of techniques.
So it connects the dots.
Yes, and beyond just explaining things, it provides a principled way to design new methods, like we saw with the debiasing strategies and influence clustering, leading to state-of-the-art results.
So for AI researchers, ML engineers, understanding ICON gives you a deeper grasp of the field, helps you see connections you might have missed, and could even spark ideas for your own work. The practical impact seems clear from their results, too.
Absolutely. It's a powerful theoretical tool with practical benefits.
All right, maybe a final thought to leave everyone mulling over. If ICON unifies so much within representation learning through this information-theoretic lens, what other areas of machine learning, maybe ones that seem totally unrelated now, might actually share a similar deep common foundation?
That's a great question.
And how could finding those connections unlock future breakthroughs? Something to think about.
Definitely something to think about.
That brings us to the end of this deep dive. We really hope you found this look at the ICON framework useful. Thanks for joining us, and we'll catch you next time.